For months, the Tesla world has been filled with rumor after rumor, but none of the speculation compares to what recently appeared on the highways of Silicon Valley. Drivers began filming a strangely shaped, heavily camouflaged vehicle cruising among normal traffic. Many instantly believed it was the long-awaited Tesla Model 2 prototype. And within hours, the footage ignited a massive discussion across the internet. What made this sighting especially meaningful wasn't just the exterior wrapping or the possibility of a new Tesla. It was the context. Seeing a prototype at this stage driving confidently on public roads signals that Tesla is testing a platform it considers nearly production-ready. Automakers don't risk early-stage prototypes on real highways unless they trust the engineering foundation underneath. And that has caught the attention of engineers, analysts, and industry insiders everywhere, even through the camouflage. Certain shapes, proportions, and shadows reveal hints of design decisions Tesla has never shown in public before. Study automotive engineering noticed right away that the silhouette and stance communicate something unusual, something that suggests Tesla is now testing technologies that experts had previously only seen in research papers, not in physical vehicles. That is why this sighting matters so much. It isn't just a secret car on a highway. It is a sign that Tesla has quietly advanced to a new level of battery integration, structural engineering, and autonomous hardware. And it is this deeper technical story that today's analysis will explore. One of the biggest surprises is visible by examining the vehicle's floor height relative to its wheel diameter. The ratio is noticeably different from Tesla's current production models. This is a clear sign that Tesla has redesigned how the battery pack interacts with the vehicle's structure. Existing Tesla models use a structural battery pack where the pack itself is part of the frame, bonding the front and rear gigacast sections together. But on this prototype, the geometry suggests Tesla has pushed beyond that concept. Instead of a structural pack, they appear to be experimenting with full cell-to-chassis integration. The individual battery cells are directly attached to the vehicle's floor with no traditional pack housing. This design transforms the car at the most fundamental level. Removing the pack housing reduces weight, increases usable battery space, improves energy density, and strengthens the vehicle's structure. When cells are bonded straight to the chassis, impact loads distribute more evenly across the car because there is no bulky intermediate layer to deform. At the same time, this approach is extremely challenging to engineer. Such a vehicle floor essentially made from hundreds of batteries must protect each cell during crashes, keep them isolated electrically, maintain safe temperatures, and allow for consistent pressure across their entire lifespan. The fact that Tesla already has a functioning prototype on public roads indicates staggering progress. If this is what it appears to be, then Tesla has solved problems that many believed would take years to overcome. Observing where the camouflage meets the rocker panels, the lower body line appears completely smooth, with no visible seams or lips where a traditional battery pack would normally attach. That clean transition strongly aligns with the idea of direct cell mounting. Conventional structural packs require reinforcement around the perimeter to connect them to the chassis. Eliminating those heavy interfaces saves weight, increases rigidity, and streamlines assembly. But it means thermal expansion must be managed across the entire bottom of the vehicle, not just inside a sealed pack. It also means Tesla needs a new way to handle crash loads. One that protects exposed cells without relying on thick protective pack armor. The wheelbase to-length ratio visible in the leaked images is another subtle but meaningful clue. The proportions suggest Tesla achieved more efficient packaging inside the floor. Industry analysts estimate that cell-to-chassis designs can increase volumetric battery efficiency by 15 to 20%. If the Model 2 aims for around 250 miles of range, gaining that efficiency could mean using fewer cells while delivering the same performance. Fewer cells reduce cost, weight, and complexity, which is critical for a budget-focused vehicle. A lighter vehicle also performs better, handles more responsively, and consumes less energy per mile. And with Tesla pushing charging speeds higher, the chemistry used in these cells likely supports increased thermal loads while maintaining longevity. There is also the possibility that Tesla's affordable EV will feature the company's 800-volt architecture. previously seen only in Cybertruck. Higher voltage shortens charging time dramatically, while enabling thinner cables and more efficient power delivery. Some camouflage around the charge port area looks bulkier than expected, hinting at new cooling components or advanced electronics for 800-volt operation. If Tesla brings ultra-fast charging to a low-cost vehicle, the entire industry must reconsider how it differentiates premium models from budget ones. Charging speed has traditionally been a luxury of advantage. With an 800-volt Model 2, Tesla could erase that boundary entirely. A shift toward cell-to-chassis integration would affect more than the vehicle itself. It would require redesigned factories, new supplier arrangements, updated crash testing protocols, and rigorous quality control procedures. It is not just a matter of engineering, but of manufacturing philosophy. For Tesla to have multiple prototypes running smoothly in the real world suggests they are validating a complete ecosystem behind-the-scenes material suppliers. Cell bonding techniques, thermal systems, repair considerations, and manufacturing scalability. Every mile these prototypes accumulate helps refine those processes, ensuring Tesla's mass production plans stay on track. As the public debates battery architecture, another major question arises. What driver assistance systems is Tesla testing? On this prototype, a glance at the roofline reveals unusual protrusions and subtle bumps beneath the camouflage. These aren't random shapes. They appear to hide new sensor placements that differ from Tesla's typical camera-only configuration. Tesla has famously committed to vision-based autonomy, even removing radar from its vehicles. But Elon Musk has recently acknowledged that certain alternative sensors might be useful for validating performance or addressing rare edge cases. The prototype's roofline hints at either advanced camera modules, higher resolution imaging systems, or even the possibility that Tesla is running internal tests. Comparing vision-only approaches with sensor fusion systems like LiDAR, that does not necessarily mean LiDAR will appear in the final production Model 2. Automakers frequently test competing approaches to gather data. Tesla could be benchmarking its vision system against other sensor technologies to improve training data, identify weaknesses, or verify system robustness. The front grille area is also intriguing. Behind the camouflage, there appears to be a redesigned dual-camera placement, possibly forming a stereo vision system. Stereo cameras provide depth perception through two lenses spaced apart, similar to human eyes. This method is more accurate in certain lighting conditions, and it is computationally less expensive than estimating depth from a single camera feed. For an affordable vehicle where cost efficiency matters deeply, stereo vision could be the perfect balance. It can enhance perception without the need for expensive hardware, while these leaked images reveal new sensors. They also imply something invisible, a new computing hardware generation. Tesla's hardware for system is powerful, but the next leap toward full autonomy requires even higher efficiency. Affordable EVs can't use expensive processors. So Tesla must design a chip that delivers high performance with lower energy use and reduced cost. The prototype's presence on open roads suggests Tesla is validating not just camera placement, but the entire pipeline from perception to decision-making to driving actions using the next-generation hardware. Every hour of testing gives Tesla more real-world training data. Every unexpected scenario strengthens the algorithms. Every unusual road condition ensures the hardware is capable of safe and predictable output. By launch time, Tesla will have tested the exact combination of sensors, cameras, and processors that customers will eventually rely on. This puts Tesla ahead of most automakers, who often validate hardware after mass production begins, not before. The placement of sensors on this prototype also shows Tesla's long-term strategy. They want the vehicle to be capable of growing smarter over time through software updates. That means shipping the car with hardware compatible with future features, even if those features aren't ready on day one. With affordability being a core requirement, selecting the right sensors becomes a balancing act. They must be cost-effective, yet capable of supporting capabilities Tesla has not even fully defined yet. while sensor placement and battery integration dominated early reactions. A third area of innovation hides in plain sight: the vehicle's proportions. Observers immediately noticed that the front overhang of the prototype is significantly shorter than that of a Model 3 or Model Y. Meanwhile, the wheelbase appears unexpectedly long for the overall vehicle size. These geometric differences are not merely stylistic choices. They align exactly with Tesla's new unboxed manufacturing approach, which was revealed during Investor Day. In traditional manufacturing, a vehicle moves down an assembly line in a fixed order. Workers and robot